Everyone, welcome back. So last time we talked about coordinate systems. So now we can actually formally begin our analysis on the various operations on vectors, right? So I thought of beginning this lecture on gradients, and then you have divergence, curl, and Laplacian. So these are some of the various operations that you can actually perform on vectors, right? And generally these are really easy scoring topics even in exams. So but anyways, so consider you have a hill, right? So this is like I'm talking in terms of three dimensions. And and let's say you are moving on this hill, right? So and you're moving in some direction, right? You can move in either x. So I mean, technically this is a 2D hill because there is no height elevation, let's just assume, right? So so the point is, um, how fast are you moving? That is the question, right? And there is a lot of answers to this, um, in the sense that we can move. So this man can move in any direction, right? So from our earlier classes we know. So let's say that f is a vector. F is a function of x and y. Okay, it is a two-dimensional function, and I it represents the spatial direction of my movement. So in our earlier classes you might have heard of theorem of partial derivatives. So it just means, right, how you can represent an infinitesimal function in terms of its spatial components. So chain rule is being applied here. So I can write df as df by dx, sorry, yeah, df by dx plus df by dy. So I can represent my spatial movement on this hill in through these components. I mean, in this way, right? So so this is just going to tell me how I am. It just denotes my movements. And I'm using partial derivatives because this represents movement in x, right? And this represents movement in y. So that is why I'm using partial derivatives, right? And so yeah, but you can also see. So let's call this equation 1, right? Equation 1 can also be represented as this way, vectorially, as dxx cap plus dy cap. Okay, and this quantity right here, right, this is the gradient of the vector. So formally gradient, so this is the del operator, right? And the gradient is just, you can say it is a analog of your slope in ordinary differential calculus. Not exactly, but it to geometrically put it, it is a vector. And it has some magnitude and direction, and it points in the direction of maximum increase of the function. So in this case the function is my movement. So whenever I find the gradient, I am denoting the direction in which I am moving the fastest. So that is the the technical term of gradient. So the gradient operator is denoted mathematically like this, right? And so now there is another technicality here, right? Well, I kind of said my movement here, right? I mean, I should have started with probably like a better example, but technically, not technically, gradient can only be applied to scalar fields, in the sense that my movement is a vector field technically, because it has direction. So scalar fields can be such as temperature, right? Temperature, and so on, right? So the temperature is a scalar field. So gradients can only be applied to a scalar field, right? So you can call it psi of x, y, z, whatever. I am working in 2 dimensions, but obviously you can extend up to 3 dimensions. And if you notice, if you only restrict it to 1 dimension, right, it will just represent your slope. You take any graph, it will just represent the slope at that point. So you can, it's more of a generalization of a slope in calculus. So that is our gradient. And so I can also write this, right? So your df in 3 dimensions, right? So if you have a scalar of phi of xyz, your gradient of your scalar is denoted as the following. Sorry. Okay. And it generally points to the maximum direction of increase. So for example, you can try on many examples, okay, but yeah, I should also probably write this down. The magnitude of this gives the slope along the maximal direction. So I am using Griffiths for reference, okay. DJ Griffiths, it's an electrodynamics book, and it's an excellent book to start off for vector calculus. So that's what I was giving an analogy of a hill, right, on a surface where you move, and so the where your movement is represented as a scalar field, and you find the gradient, and the gradient actually points up to the maximal ascent or descent, for that matter. And obviously, if your gradient is 0, it would mean that point is a stationary point. So that is a thing here, right? So next is divergence. So relatively, divergence is a much more simpler topic to understand, in the sense that again it is an operator, right, and it is again represented in the form of a del operator. And so this time divergence is represented as, so divergence can only be applied to vector functions, okay, but the divergence itself is a scalar function. So what do I mean by that? So again, you know that your del operator is d this second distance, okay, a vector functions mean fi cadence, right? And I dot this with some, so I am working in 3 dimensions now with some vector, okay, I won't write it like that, dot, and then I'll write it here, so it's dotted with this. So fx x cap plus fy y cap plus sz z cap, okay. So your divergence, so once you dot it, it will become the following, and this is divergence, right? Okay, this is divergence. So again, so Griffiths again gives you something called a geometrical interpretation, right? So geometrical interpretation, so you might want to look into it. right? And what he says is that, he says that um, it basically represents how much a vector valued function spreads out from a point. So you have a point, and it's how much it spreads out, right? So, and how much it spreads out. So you have a vector function, a vector field, to be more precise. It basically, the divergence is a quantity. So since it's a scalar quantity, so this is a scalar, this entire quantity is a scalar, so it is a number. So this number is going to represent how much a vector function is going to spread out from a point. So if it is positive, it spreads away from the point. If it's negative, you can say that the vector field is going to converge. If it's positive, it diverges. If it's negative, it converges. So you can assume this as a sink if it's negative, if the value of divergence is negative, and if it's positive, it is a source because it is emanating from that point. So that's all for divergence. And the last operation, well, I mean, this is the second last. The curl is there's also something called the Laplacian, which we will look into. So the other operation here is curl. So formally it is defined as this determinant, right? Again, I'll stick to one notation since I'm using f. So fx, fy, fz. So it is just this determinant, and it represents how much it curls around a point, right? So you have your axes here, and you have a point here, and this curl is going to, this vector operation is going to determine how much the vector is curling around a point, right? And so this is how, so this is another operation, right? And you can think of it like a whirlpool, and that is swirling up to a specific point. So that's that. So yeah, and generally you have a few properties of these functions, right? And so I'll be continuing this in the next class.